So now that you have a model that's making predictions according to some distribution, you're going to be producing answers, classes, or predictions, or labels. And an inevitable question will be not just, is it accurate, is it working, does it do what we do, but is it significant? And this is kind of like a dreaded question, but also one that is easy or possible to prepare for. Any machine learning researchers and students will get familiar with it because it comes down to a contrast in different ways of doing things in, say, in statistics and in math, than in machine learning and computer science and some parts of engineering. There are multiple ways to assess the performance of a predictor, of an algorithm, and they do different things, and they're useful for different purposes. An important one is hypothesis testing. Next slide. So why do we need to talk about the significance of our result? So kind of not really a secret, but something to remind yourself every once in a while, that the processing of the data and the making the predictions and getting the classification, even having a high accuracy on some test, which is something you'll be focusing on in the assignments and you'll get drawn into in many things. You hit a particular metric, high accuracy say, and that's great, but is that the end goal? The end goal, right, has to be understanding this data or interpreting the data or having it produce something useful. And it's also having confidence that your analysis and your answer is correct. And maybe most of the time you can't guarantee it's going to be correct because this is an optimization. We don't know usually the full model of the system we're talking about. We have the data, but we don't have a physics model of this domain, or it's too big, or it's genetics and no one knows the actual underlying thing, or it's language and there is no underlying model. But you want to be able to say that your answer, your prediction, your labeling is plausible or highly probable, right? And so while this idea of significance is one way of getting at that, we were talking about the distance between two distributions, whether your new distribution you've learned from the data is similar to another one. That's one way to do it, but significance is another way. So what is hypothesis testing, which is this mechanism that gives us significance? The idea is that given a known distribution, we'll call that D0, that produced the data, we could put forward a null hypothesis saying this is what creates the data, that's the thing that we're expecting to be the generator of the data, and you can do a significance test to figure out whether this hypothesis is correct or not, or probable or not. So if we put forward, we're going to have different types of hypotheses, but say we're putting for this first this null hypothesis saying we're going to assume that this particular distribution D0 is what generated the data. Now we could say D0 is a Gaussian, right? So we've got our N01, which you should be familiar with now, is a Gaussian with mean 0 and standard deviation 1. And the sample we get out of, we pull one sample from this and we get X, right? So we've got our Gaussian at this, and it's a very boring distribution. It's perfectly symmetrical, even though I'm not drawing it perfectly symmetrical. And the sample that we draw is 2.576. Right, this is the number that we get out of it. And we want to know, is this plausible? Is it really a Gaussian? Is this what we've got from here? And then we compute this probability, right? So we can compute the probability mass and say what portion of the data falls under this part versus that part, right? And so if we do that, we say what's the probability of a sample U taken from this distribution Gaussian being less than the number that we got. and we get the answer that there's a 99% chance that any sample you pull will be less than that. So this number is greater than 99% of all the points you would expect to get, right? And so this is not a very likely sample. And so if the thing you're pulling from generates samples like X, you might be able to say that this is not a very plausible hypothesis, right? And so in this case, we could say the difference between the sample X from the assumed distribution is statistically significant because we gave we'll have another value here, which is P. They usually do the reverse of this. The P is the probability of that U 1 minus it. So in this case, it'd be 0.1 or 1%, right? And so if you're setting a 1% p-value, significance value, you're saying, I'm going to reject things that, unless they hold for 99% of the data, right? Whereas in this case, this X did not. So that's a kind of a mechanism that we use, but how do we use it to prove or argue that our models are significant? So we generate a few hypotheses. So we have the alternative hypothesis, kind of starting at the end and moving forward, but it seems to make a bit of sense. This is the hypothesis that you believe to be true. So if you're trying to show that your model gives a prediction that is kind of more efficient than other ones, or that the prevalence of this disease is growing because of some feature that you've observed in the data, you're saying this is our alternative hypothesis. And then you put forward a null hypothesis, which is what if we're wrong, right? And so in logic, the null hypothesis is just the negation of the alternative hypothesis. If this thing is false, we have some other hypothesis, and that's the one we're going to test, right? So we're going to say, let's assume we're wrong and see if it fits the data. And if our data is outside that world, then that means we're in this situation where the hypothesis we gave is very unlikely given all of this, and therefore the alternative hypothesis is correct, which is what you want, because your alternative hypothesis is yours. So what we want to be able to say is that sample X lets us reject the null hypothesis with a 0.1 confidence level, which says that the model is 90% correct, which is different than what I had in the previous slide, which is the 0.01 confidence level. Right, so you can set that number to be whatever you want. A lot of times, kind of the common thing, at least in kind of biology, is that this confidence level is set to 5%. So if you can explain 95% of the data, then you're doing pretty good. In order to specify the null hypothesis, we're just going to look at one major one, this chi-squared test, which is good for discrete data and has a Gaussian assumption. There's an alternate form of this using the student t-test, which is also based on chi-squared, kind of just for one limited case of it, which you can also kind of look into on your own. But we'll explain the overall idea of the hypothesis test as an example using the chi-squared distribution. The chi-squared test, and so chi, did I have it here? I have it here. This is chi. It's in LaTeX. It's just chi like that. Greek symbol chi, not x. It looks like an x. So this is a statistic measure, which is defined in this way, and it measures or represents a Gaussian assumption about the data points. So we're saying that we have a number of classes that our data belong to, and then when the data are sampled, they're kind of sampled with a Gaussian distribution in mind. So the data points for every class are sampled as a Gaussian. I'm trying to make it look like there's more points near the center, which might not be exactly how it looks. The way it's computed, given the data points, the features, and the labels, uses all of these counts, right? So the O's and the E's we're going to explain coming up. These are the observed counts and the expected counts. Essentially, how many times do you see this data point or this feature for every feature and every data point? How often do you see it in a particular class? And how often would you expect that to occur given the assumption of Gaussian kind of randomly assigning data points to all the classes from a Gaussian distribution and being able to sample completely uniformly from all the different classes, not uniformly, sorry, independently and identically distributed from every one of these classes so that there's no memory of which one you've taken previously, right? So these are both very strong assumptions, and so that the chi-squared gives us a null hypothesis that is kind of this very unreasonable but well-defined and easily to test measure of how you would assign points to classes if you kind of randomly throw them around. And so the idea is, if this is your null hypothesis, then you'll get, if your model is much better than at predicting the class assignments than this model is, then you get a high value of chi squared, and you'd be able to reject the null hypothesis, which would give you a higher confidence that your model is good, right? But it's good in comparison to this very kind of toy model, but sometimes there's models that are like, well, that's not very great, but we surely should be able to beat that, right? So if you can't get a high significance test against this, then your model isn't very good, or there's something particularly weird about your data that this is actually realistic, right? So what are these O's and E's? The way we get these is, this comes up multiple different times in the course, so I don't know if you've seen it yet, but you will see it again, or you have already, is this idea of a contingency table. So in this case, we've got our features on the rows and our labels on the columns, right? And so we're saying if you have a number of, when you pulled a whole bunch of samples from your data pool, right? So say we've got all our original data points in some kind of container, which is where they begin, and then we have 3 different classes, and each time we're sampling them, they're going into one of these bins, right? And we're sampling and we're getting a certain number of points in all the different bins, right? So once you've done all that, you'd have a count, right? How many samples did you see for a particular class? Also for every class K, right? So we'd have this entire table for YA, for YB, and for YC, if we have the 3 classes A, B, C, right? Then you'd have these counts. You'd say, well, how many of the samples in the class have this particular feature, right? So we have a number of features that describe our data. So if it's a population, it could be, neighborhood, income, language spoken, favorite TV show, various features. And so we have all the counts of how many of the points that are in this class have the feature, how many of the points don't have the feature, the number of samples in other classes that have the feature and don't have the feature, right? So you're covering for this particular feature where they all reside. Are they in A or not? And is the feature relevant, right? So right, in this case, right, rows and columns. Right, these ones all have the feature that we're talking about, right? So in this particular point, let's say that the feature is age, right? And we want to predict something based on age, right? And this doesn't have the feature. And then this is whether it's in the class or not in the class. Right, so we're counting, this is all the situations that occur. So that's our O that we're going to use here. So how many times did it show up for various different features? And we're going to sum over all the different features and classes, but get the statistic for each one. and then E. Okay, so what are the E's? The E's are computed from the observations, and they really are normalized values of the kind of all the support of each entry, right? So when we're looking at, if we look at E11, which is, if we go back to our formula, which we're going to need for our chi-squared, the main part above the denominator there was going to be this, and I'm going to divide this by EIK, right? So we have, for every observation, O11, right, and that's what our OIK is here, we're going to have a corresponding E11, right? And so for this one, what we're doing is we're taking the O1 and the O21. I should have all of those here again, so as a reference. Maybe I'll update my slides later and give you guys the validated one. Right, this is our breakdown of those. Ooh, I don't do that. So we're saying that we're going to use add these together and add these together and then multiply them, right? In order to get the normalizing for this, and we're going to divide it by n, which is all the data points, right? So when we do that, what we get here is the 104.6, right? So it's kind of most of your weight. You've got 100, and you're normalizing it based on how much of all the other, basically all the objects in the same class, ignoring the feature, and all the data points with the same feature, ignoring the class, and then divide that by n, because obviously these would add up to more than n. And say, well, what kind of proportion are you normalized in, right? So our expected probability, essentially, of when we use this data as our distribution, we're saying that 100 out of 104.6 gives you kind of the ratio from our observations from what we would expect, from what the total expectation would be, right? And on some of them we're kind of close, and some of them we're not that close. Right, and here's our n's that we're going to need. The n for all the data points is there. Yeah, so those are what those numbers mean. But then how we use it, if we go back to this formula, then on the next slide we have it all calculated out with these numbers. So say these are our observations that we got from our of our 4 classes for some particular feature, and we compute the O's and the E's, and so now we're taking the differences, right? So that original formula we had sums over, right, every one of the features, right? So this table here is just we're summing over every element of this table, right? So for every one of these, we're going to compare it with its corresponding expected value and do this difference, this square, and normalizing again by E, and we go on to get this entire value, right? If we go back to the original formula a few slides ago, that's where this is coming from, right? We're summing over all the different features and labels, and then computing this for each one and combining them, right? And you can simplify that down to say that we're essentially summing over all the features and labels and doing this ratio of the outcomes with probability counts instead. So the number of degrees of freedom here is 1, and once we know that and we have this kind of value, here's the chi-squared value we got, we can say now, is it significant enough? So to get that calculation of probability of that sample coming from a distribution with these particular observations, we can set our p-value that we were talking about before and say, well, what level of significance would we have to basically accept in order for this data to be normal, quote unquote, or significant, right? And so we have a table in the next slide. It's a little pixelated. So we're saying in this model we've got degrees of freedom 1, and what number did we get? We got 1.51, and so we're in here, right? And that would mean we'd have to have a p-value in between 0.3 and 0.2, right? And so when we compute it out exactly, to say that is that we'd have the chi-squared 30, yeah. So we can claim that we have a 0.3, a p of 0.3, or a 30% significance rate, right? Which again, right, means that 70% of the data would be consistent with this. With this model, even if it were modeled as a Gaussian. And we can't claim more than that. So if we wanted to have P5 and say that our model handles 95% of the data, and that's how much data you have to have for the null model, the null hypothesis to be true, then we'd have to get a value here of 3.8 after we run this formula. So that would mean these numbers have to be even better, matching the expectations. So these differences are more significant, right? So it's actually that we want the differences here to be bigger, right? Because squaring is going to get rid of the negatives. So we want some of these to be surprising, because if we just follow the normal distribution and kind of average it out here, we're assuming we would get this, right? If our name came out exactly like this, we'd get 0. And you'd be like, oh, it is definitely the null hypothesis, right? But if this thing is getting a different answer, then it will diverge from that. And if this is the outcomes, or where the data is really coming from, this is the true distribution, right? The observations are the reality, and we want to show that it's significantly different from the null hypothesis, which is this Gaussian assumption. So, like I said, hypothesis testing is one method that is commonly used. There's lots of variants of how to use it, so you can kind of read up. There's entire huge literature about it. It's used a lot in medical research and clinical research, and like psychological and other studies, especially with human behavior. It's a difficult method to use. It's kind of built on classical kind of statistic ideas of frequency of observations. So a lot of the things that I will talk about, and you'll see more in machine learning, come from a more assumption of a Bayesian distribution. So we'll talk about alternative ways to do this kind of confidence interval evaluation using Bayesian methods. And that's where you say you have some kind of a model or assumption, and you're not just counting the frequency of points, but saying what are the expected distributions and differences from those. All of these methods can have bias and be misused, so hypothesis testing has its own tricks, problems. There's confusing terminology, this whole null hypothesis, and rejecting the thing that you want to be false so that you can prove the thing you want to be true. It's a little counterintuitive, and so it's easy to misuse it and say that you're having some very significant result as a result, even though it doesn't actually match what you're doing. It's no replacement for a controlled causal study with a control group and sample group. So all the testing they're doing for the vaccine don't come about just by looking at a bunch of data and doing significance tests. They have actual different populations of people who are given the vaccine or not given the vaccine, and you're kind of control each of the conditions and all of the properties of those people in order to have the distributions controlled so that they're the same group of people, and you hope that it carries forward. But once you have that done, you can use these tests to kind of give you significance of each element, but they don't tell you whether something causes something else. It's always correlational. it's unfortunate the word is significance, because in English and in language people think it's like, well, how significant is your data? Significant? Oh, it's point 0.1. It's very significant, right? That's not what it's telling you, right? It's telling you what? What is it actually telling you? If you think about it for a moment, right? This approach, is it telling you how significant your predictions are? Right, what it's actually telling you is something more like, how different is the predicted output, if your observations you're seeing are the labels you're getting from your algorithm, how well do those match with this Gaussian expectation assumption? And it doesn't necessarily mean that yours is better or that it's correct. It just means that it's more predictive than this other model, which has these particular properties. And it has some other hypothesis tests in general have some properties that as you get more data samples, you essentially get a higher confidence because of larger data samples and just the law of large numbers. Eventually, your observations will match the data better on these kind of broad assumptions. And so the way the calculations work, those averages get kind of washed out. And so if your precision goes up or your number of samples goes up, then your confidence will eventually go up. So if you collect more data, your model will get better. And that can be true because you have more data and your model is able to find patterns that aren't there. But this is true regardless of whether your model is good or not. So even a really bad model with huge amounts of data could get a very high significance level. So you have to scale the confidence level you have based on the data, right? If you've got billions of samples, saying that you only want a p of 0.5 is not very impressive because you have billions of data points, right? If you have some medical thing with just thousands of patients, this could be very hard to achieve. But with the internet and Twitter data, this doesn't make any sense anymore because you can find anything if you only want to be 95% correct, better than a Gaussian assumption. So this seems weird, but it's not, and a lot of people try to denounce these methods, saying they're kind of basically useless because of these things, but if you use them properly and set them up in the right way, which again is not really my expertise, but there's a whole field of people who use it in very strong ways, it can be quite informative. And machine learning's assumptions often rely on IID or Gaussian assumptions just as much. Right? Everybody assumes Gaussian because it makes the math work, and they try to get away from it, but a lot of times it's based on that, or it's based on IID, which is saying that every time I get a new sample, I have not been influenced by my previous samples in any way, which often isn't true, right? Because you may not be resampling, and the frequency of the samples you get or the observations you get would not be true, right? So if you're doing like an autonomous driving system, none of the data is IID, right? All of the sensors are correlated by the world that you're in, and they're even related to events that happened seconds ago, minutes ago, hours ago, right? They relate to the driver who remembers what happened. So IID is not true in the real world most of the time. And in some cases, you can make show that this is equivalent to this Gaussian uniform distribution kind of assumption of hypothesis testing. So they're both wrong. But they're kind of some of the only things we have. And so building better models for confidence building, confidence estimation, being sure of your model's performance. These are all things that are actually hot areas of research and very hard questions to resolve, especially in machine learning as we go into more deep learning these days, because those models don't give you any guarantees or any distributions most of the time. They just work and they give you accuracy, so even this thing can't work on it. So it's a hot area of trying to improve, and it's really a criticism that comes to a lot of machine learning, but also a lot of statistical methods, that if you do these things wrong, you get overconfident about things, and there's crises in certain areas of science because of these methods being applied incorrectly, leading to those kind of problems. So all that to say that it's useful to know and to be cautious about it, but if you're doing experiments and trying to show it, there is a right way to do it, and someone might ask you, is your result significant? And you should be able to answer them in a sensible way. So there you go. Hopefully that will help. Next topic.